Welcome students, my name is Dr. Praneeth, and today we will see about the third part of cycloalkanes, and in this especially we will discuss about the stability of the cyclohexane in this class. So let's move on to see this cyclohexane stability. So here I have given some of the cycloalkanes which we are already familiar with. Like this is cyclopropane, this is cyclobutane, this is cyclopentane, which is having 5 carbons. Like that, this is cyclohexane, cycloheptane, and cyclooctane. We already know the structure, how the structure looks like, how to calculate the general formula of the cycloalkane, and how to calculate the molecular formula of each of the cycloalkanes. So in this class we will see whether what about the stability, right? In this class we see the stability of the cycloalkanes. For example, we can compare cyclopropane and cyclobutane, and we can raise a question which is more stable, whether it is cyclobutane is more stable or cyclopropane is more stable, and why it is, why one of the cycloalkanes is more stable than the other one. So this is a basic question we can raise if we talk about stability, right? So in this, let's see how we can define stability based on some theory. So for addressing the stability, the German chemist Bayer proposed a theory to predict the stability of the cycloalkanes. So what is the theory? And this theory is proposed very long back, 1885, when still still we can use this theory for some cycloalkane, whether to predict the stability. But some we cannot. This theory also somewhat not is incorrect in some of the cycloalkanes. We will see in detail about these things. So what the theory says, so Bayer-Stein theory says that tetrahedral bond angle, that is carbon with four bonds, right? Four groups attached on one carbon. Like say methane. Methane is having carbon and then CH, four hydrogens around that, and if that will make a tetrahedral the geometry, right? And this tetrahedral bond angle, that is 109.5, is more stable in the case of cycloalkanes. That means if you take a cycloalkane and if you measure the angle, the bond angle, if it comes to 109.5, then that cyclohexane is more stable. This is what the theory says, and here I have shown the diagram here, the tetrahedral bond angle. You can see here, this is a methane and this is carbon, and it is connected to 4 hydrogen atoms. The angle it makes is 109.5. That's why the methane is very stable and is very difficult to break these bonds, each of the bonds. So any deviation from this tetrahedral bond angle causes an angle strain in the molecule. So if you take any cycloalkane and if the bond angle is more than 109.5 or less than 109.5, that means it will have an angle strain and it is not stable compared to the ideal bond angle, which is 109.5. So strain will increase with increase in the deviation. So if what is this meaning? If the bond angle is difference is more. So if you for example, if a cycloalkane is having a bond angle of 100 degree, and you can subtract this ideal bond angle, that is 109.5, you will get 9.5. That is the deviation value. That is the difference. So that is 9.5 will get the difference. In some other cycloalkane, if the difference is for example, let's say it is 20.5, that means the 20.5 deviation is more, the strain is more there. That means it is less stable compared to the one which is having the difference of the deviation angle less. That's what is meant. Strain will increase with increase in the deviation. So the angle strain will increase if the deviation, that is the difference, will be more. If the difference is more, that means that will be less stable compared to the one which is having a less value, that is the deviation value. So these things we will see in examples also. So what is the take home message of the Bayer's chain theory is, if cycloalkanes, any cycloalkane possess this ideal bond angle, that is 109.5, that is more stable compared to the one other alcohol cycloalkane which is having a different bond angle, that is less or more of the ideal bond angle, which is 109.5. And also any deviation from this ideal bond angle will cause us an angle strain. The deviation value is less, that means it is more stable compared to the cycloalkane which is having a more deviation value. So this stability we can check in this two example. In this slide I have given two molecules, two cycloalkanes. One is cyclopropane, the triangle shape we already know, and how many carbons are present here? This is 3 carbons, right? 1, 2, 3. The 3 carbons are present, and this is a cyclobutane which is a slightly more larger molecule, because it having a 4 carbon, 1, 2, 3, 4 here at the corner, and also having a more hydrogen compared to the cyclopropane. So now the question is, which is more stable, cyclopropane or cyclobutane? You can see the bond angle, the triangle. You can see in the we know that from geometry, mathematics, the triangle, each corner, the bond angle of the each this corner is 60 degree, right? And in the case of the square, the bond angle will be 90 degree, right angle, right? This is 90 degree. So cyclopropane is having a bond angle of 60 degree. That means a carbon, 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 this bond angle, this 3 carbon, 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 carbon bond angle. And also again here the cyclobutane is having a 90 degree, this carbon, this carbon, and this carbon, this bond angle. This same here also. Here also will have the same bond angle, here also will have the same bond angles, here also will have the same bond angle. So which is more stable? What we can do is we can calculate the deviation angle, right? We can calculate the deviation angle. How we can do this? Here I have shown here. For cyclopropane, you can calculate the deviation angle by subtracting from the ideal bond angle value, that is 109.5 minus 60 degree. What is the deviation value you will get is 49.5 degree. This is the deviation angle you are getting for the cyclopropane. Let's check this cyclobutane. For cyclobutane, we have 109.5, that is the ideal bond angle, minus 90 degree, which is this bond angle of each carbon bonds. So what we will get is 19.5. So you can see here clearly that cyclobutane is the deviation angle is very low, relatively low compared to the cyclopropane. Cyclopropane is having around 50 degree, that is a bond angle difference deviation. Here it is only having a 19.5, that is around 20 degree. So there is a 30 degree difference in the deviation value. What is the meaning is the cyclobutane is more stable than the cyclopropane. This clearly indicates that the cyclopropane is more stable compared to cyclobutane. Cyclobutane is more stable compared to cyclopropane. Same way, we can also calculate the cyclopentane and cyclobutane. Here I have shown the planar structures of cyclobutane. This is cyclobutane and this is cyclopentane. Take the 5 carbon here, 1, 2, 3, 4, 5 carbons. Again, we can ask the same question, which is more stable, cyclobutane or cyclopentane? The cyclopentane. But there is one important thing to be noted is, cyclopentane, even though it is drawn in a planar geometric structure like this, actually in 3D structure, if you see the actual molecule how it is present in the 3 dimension, it is not planar. Right, it is not planar, it is an envelope form as shown here. You can see here there is a cyclopentane, there is 4 carbon here, 1, 2, 3, 4, and there is an envelope, and the 1 carbon is here. So it's like an envelope. So that's what is shown here. So 1, 2, 3, 4 in one plane. This is one plane, and the 5th carbon is in the other plane. So it is like then in an envelope type. So if we calculate the bond angle of each of these 3 bonds, like this bonds, carbon, carbon, carbon bond, or this carbon, carbon, carbon bond, or even here 1, 2, 3, this carbon, carbon, it comes to 108 degree. 108 degree is very close to the ideal bond angle, that is 109.5, right? So we already know that cyclopentane is more stable than cyclobutane because it is very close to the ideal bond angle value. Now we can see here how to calculate. We can calculate the deviation angle, right? We can calculate the deviation angle from the ideal bond angle as shown here. So we are not using this planar structure, the cyclopentane planar structure we are not going to use, but we are using this envelope structure which is the actual structure of cyclopentane, and we will calculate the deviation angle. If it, on the other hand, if we take this planar structure and calculate the deviation angle, it will come incorrect, because here if we use the planar structure, it will be around 118, 119 degree, right? So this planar structure we cannot use it because of this problem. So we use the actual structure only for the cyclopentane. So let's calculate using the actual structure of cyclopentane with the cyclobutane. Cyclobutane is 90 degree and this is 108. If we calculate the cyclopropane, what is the deviation you will get? The deviation you will get is 109.5 minus 90 degree, that is 19.5 degree, right? We already did this. So this is cyclobutane. And what about the cyclopentane? Cyclopentane is 109.5 minus 108. Cyclopentane is 108, right? Cyclopentane is 108. That is meaning is you will get very low deviation value, that is 1.5. This shows that cyclopentane is more stable than the cyclobutane. So in this way, you can use the Bayesian theory to calculate or predict whether which is more stable. Right? This is very important, the stability calculation. If you know the stable, which is more stable, then you also know the reactivity. The one which is having a least stable, you can easily react, right? But this is not stable. If it is more stable, that will not react. In the case of reactivity studies, this is very important parameter to know the which is stable, which is not stable. So cyclopentane is more stable than the cyclobutane. This is the conclusion based on the deviation calculation. So next we will move on to the cyclohexane. So cyclohexane is stable or not, right? So this is the planar structure of cyclohexane. We can see that in this angle, that bond angle of the cyclohexane is 120 degree. So this is a planar structure and this 120 degree, and you can see that the deviation of the cyclohexane is 109.5 minus 120 degree, that is minus 10.5 it is coming, right? A negative value is coming. So Bayer explained that, Bayer told what Bayer predicted is, because it is a negative value is coming for the cyclohexane negative value is coming, due to the negative angle strain and flat structure, this is a flat structure or planar structure, cyclohexane is very unstable. This is what Bayer predicted, right? So he calculated the deviation angle, the deviation value, that is coming in negative, and also the flats, because of the flat structure, cyclohexane is very unstable. That is what Bayer predicted. So this made an important conclusion for the Bayes theory, that is, it is also having a drawbacks, because Bayer proposed that ring systems smaller than cyclopentane are unstable, larger than unstable. So if we go to Bayer, what is predicted is the cyclohexane, cycloheptane, cyclooctane, they are very large molecule compared to, they are larger, more than 5 carbon atoms present, they are unstable. So based on this, he proposed that it is very difficult to prepare this higher ring system, larger, which is due to the large deviation from the ideal bond angle value, that is 109.5. So cyclohexane, we have seen that there is a flat molecule and it is having a bond angle of 120 degree. So here it is, the ideal bond angle value is 109.5 degree. So it is having a much larger deviation, because it is a larger molecule and also the very planar structure. So he proposed two important things, that is cyclohexane, cycloheptane, so larger molecule than the cyclohepentane, that is cyclohexane, cycloheptane, cyclooctane, nonane, cyclodecane, they are unstable and are very difficult to prepare because of their instability, because of their large deviation from the ideal bond angle value. However, Bayer was incorrect because about the cyclohexane and higher ring molecule. Why? Because they are stable and they exist. We can prepare this. So when Bayer proposed this theory, it was very long before it, like in 1888, 85, right? Is more than 130 years old. That 125 years now. But later, in the 1990s and 1980s, and all, people understood that cyclohexane exists, and cyclohexane and other also higher link system also can be prepared. So this is the important drawbacks of the Bayes theory, that is these 2 points. So we will see how the cyclohexane is stable. Why the cyclohexane is stable? Because Bayer proposed it is unstable. Why it is stable? And also we can also see the higher ring system like cycloheptane, octane, cyclononane, like that, how it is also we can prepare and why it is also stable. So we will come back again the cyclohexane stability, right? So Bayer proposed that it is a flat molecule, it is having a bond angle is 120 degrees, so it is unstable. However, if you see in actual structure of cyclohexane, it is not the planar structure, not the flat structure, it is a chair-like structure. So you can see here, this is a chair-like structure, right? This is a chair, and this is the actual structure of cyclohexane. Why? How we can get the actual structure? We can use the X-ray structure, right? You can grow the crystal and you can do the XRD analysis, and you can get the structure. So this is the actual structure, and you can see the bond angle here, all the bond angle, right? This bond angle, this bond angle, this bond angle, this carbon, this carbon bond angle is 109.5, which is the ideal bond angle, right? Proposed by Bayer. So the cyclohexane is having an ideal bond angle, so it should be very stable compared to other cycloalkanes. Same thing here, this carbon, this bond angle also 109.5, and this carbon bond angle is also 109.5. So all the bond angles in cyclohexane is 109.5, which is the ideal bond angle proposed by Bayer, and this is the reason why the cyclohexane is very stable compared to the cyclopentane. So you can easily calculate the deviation angle now. The deviation angle is 0 degree. Its ideal bond angle is 109.5 minus the actual bond angle of the cyclohexane is 109.5. So the deviation angle is 0. So it is highly stable. So this is the reason why the Bayer theory fails in the case of cyclohexane and higher system like cycloheptane, etc. So far we have seen that the stability, how to predict the stability of the cycloalkanes, right? Cyclopropane, cyclobutane, etc. by using the Bayes chain theory, which the main important point for the Bayes theory is the main important point is the ideal bond angle should be 109.5. If it is the bond angle deviates from the ideal bond angle, it will be unstable. And we have also seen the drawbacks of the Bayes theory. That is, Bayer proposed that cyclohexane is not stable due to the higher deviation. That is, the bond angle is 120 degree, whereas the higher system. But actually, cyclohexane is stable because it is not the flat structure; it is a chair structure, and it is having ideal bond angle actually. In fact, 109.5, so it is very stable. So this is what we have seen today, and in the next class we will see how to calculate. We can calculate the deviation angle, and we can also see why the cyclohexane is very stable, not because only of the chair structure. It is also having other properties. We will see in detail about how the cyclohexane stability, and also we will see about the other forms of cyclohexane, that is boat structure, And we can also compare the higher system like cycloheptane and cyclooctane and even cyclodecane 10 with carbon, and we will compare what is stable and how it is stable larger ring system. So this is what we have seen today, and I will see you in the next class. Thank you.